So we have been covering the special type of differential equation called partial differential equations. And the subject is really a rather difficult subject, right? So some of you might have still some trouble with that. So why? So why we are learning these partial differential equations? That's the question you can ask, right? And subject is not easy, and for some of you it could be really difficult. For engineers like yourself, the purpose of learning partial differential equation is for most of all for the money. Money is the money, right? For the money, right? So money includes many things, like building a good bridge. So if your solution for the particular solution for partial differential equation is wrong, then some bridge can broken, right? Bridge can collapse, or somebody who going to go to Samsung or some LG Electronics, and if you design something, some circuit, and if it gets wrong, then your device will fail. So today I'm going to focus on money. And it may be a good opportunity to find that partial differential equation can be actually applied for the money, or called finance. So in finance, most important thing is asset, like a stock. Stock is 주식, or bond, is 채권, etc., etc., etc. And we know that, for example, if you take a look at time, and this is stock price, it goes something like this, right? So if you take a look at each interval, it's a random motion. So if you take a look at closer look at certain interval, it's more like this price is a random motion called Brownian motion. So it is it's hard to predict what the stock price will be maybe year after, right? So there are another way of the risk management is set some price. Say this is some price called, say, X. You want to say X T at T star. So this one way of the reducing the risk is having call option. It's a right to buy on asset or stock at striking price of C at time t star. This time is called maturation date. So if at maturation date T star, if the stock price is over C, then you can buy the stock at the price of C, right? If it is lower than C, then you don't buy. That's the way that you can reduce the risk of your investment. So we can say time T star, we call WXT as option price. Then XT star is X minus C over 0 if X is over than C. Then X minus C is the profit that you can make with the option, right? So two things, XT and WXT is used. This is called option price. Time T and stock price X used to minimize the risk. Mathematically, that can be written as the following portfolio: pi xt minus partial x partial omega xt omega xt. This is a hedged called hedged portfolio to minimize the investment. So minus sign is the selling. So at a certain time t, you buy xt and you sell option divided by the partial derivative of option. Then we are in a free economy. The change of hedged delta t is delta x minus partial omega partial x delta omega xt is supposed to be proportional to the interest rate delta t are x minus partial omega partial x partial omega omega delta t. This r is interest rate. So in a way, finance is more like a physics, it's based on assumptions. The thermal equilibrium assumption is actually called non-arbitrarity assumption, but I'm not going to go to details, just the basic concept. The stock price actually, xt is in the Brownian motion, right? Or called stochastic process. Which you are going to learn maybe next year. The random and stochastic process is a really important subject for the signal processing. And so we are not going to go details, but we are going to do some simple things. So delta x t is interest rate x t delta t. So change of stock price will be driven by the interest rate. Plus this is a stochastic fluctuation with such that epsilon square minus epsilon square is equal to 1. And this is called the average. So I guess you learned about the probability and statistics in high school days, right? So you know how to calculate the average. And this epsilon is actually 0. So this is the change of a stock price over time delta t using the Brownian motion analysis. And for now, you need to believe me. So this is actually, in order to derive this part is a bunch of different mathematics, and we don't have enough time. So we are going to use this result from the Brownian motion analysis. So this is important result, just believe me. Then, interesting thing is, delta x square is proportional to r square x square delta t square plus phi square. This phi is degree of stock price fluctuation called volatility. X square delta t plus twice over r phi x square delta t square delta t. So as delta t goes to 0, then delta x square is proportional to v square x square delta t. So this is a really important result from the Brownian motion analysis. So if you are learning the probability and random process next year, I think you're going to learn about this Brownian motion or Wiener process, sometimes called Wiener process. So using this knowledge, let's go back to the change of option price. So I'll try to go as slowly as possible. This is a new concept, and I'm going to show how this works. Analysis. So let's go back to the hedged portfolio. Then delta x minus delta omega xt x omega to the first order. Then delta omega xt can be expanded using Taylor series. Delta x delta omega delta x plus 1/2 square plus partial t partial omega delta t plus etc. And previously we learned that delta x square is proportional to v square x square delta t, right? From previous. So if we put this into here, this becomes partial x partial omega delta x plus 1/2 v square x square partial x square partial square omega delta t plus partial t partial omega delta t. So delta x minus partial omega partial x delta omega xt is the following. Delta x minus 1 over partial x partial omega partial x partial omega delta x plus 1/2 v square x square partial x square partial square omega delta t plus partial t partial omega delta t. And we can see that this cancels this, right? Because of you divide by, if you here, if you divide partial omega partial x by denominator, it's just delta x, and this cancels each other. And this has to be the same as, according to our assumption, x minus r omega partial x delta t. So if we arrange the terms here, and we can multiply this on to the right hand side. We have the following formula: minus 1/2 v square x square partial x square partial square omega plus partial t partial omega minus delta t is same as r x minus partial omega partial x omega partial x partial omega delta t, same as r x partial omega minus r omega delta t. So if we cancel delta t everywhere, then do we have enough space here? So this is 2, this is 3. Then what do we have? Rx partial x partial omega minus r omega, same as minus partial t partial omega minus 1/2 v square x square partial x square partial square omega, right? And okay, let's have another space here. This is 4. So if we move this, rearrange the terms, we have the following partial differential equations. This, which is partial t partial omega is RW minus Rx partial W minus 1/2 V square x square round x square round square omega. So someone discovered that the price of option can be found by solving these partial differential equations in 1973. So let me just write down. So summary, option price at time t with stock price xt. Then the partial differential equation is satisfied as partial omega xt is rwxt minus rxt partial x partial omega minus 1 v square x square partial x square partial square omega. So this equation was actually discovered in 1973 by Fisher, Black, and Marion Scholes. In Journal of Political Economy. In 1998, Marion Scholes received a Nobel Prize for discovering this equation, because this equation changed the world of finance. And before this equation was available, the finance was like art. So you trade your stocks and based on your instinct, calm. But after 1973, you can just solve the partial differential equation to predict the price of the option. And after that, the new era of engineering called financial engineering was born. So this actually was beginning of financial engineering, or in Korean called 금융공학. Unfortunately, the Fisher Black died in 1995, so he couldn't get the prize, and so only the Scholes got the Nobel Prize for this equation. But this equation is called Black and Scholes equation, so this has a name. Black-Scholes equation. The option price. So it looks like learning partial differential equations has something to do with the money too, right? So I hope this topic will motivate a bit of why you are learning engineering math, especially this part, partial differential equation. So I'm going to spend maybe today the solution of this following the way that the Black and Scholes did about 45 years ago. So I'm going to change one variable called, so let's start with volatility V sigma. It's more modern terminology. So then the Black-Scholes equation will be simply the following. Partial t, partial omega is r omega minus rx, partial omega minus 1/2 sigma square x square, partial x square, partial square omega. R is interest rate. So the Black-Scholes assume that interest rate is constant, but it's not. So assumed constant. And the boundary condition is the following. T star this is a boundary condition. Actually, it's a future boundary condition, not the initial condition. So it's called the final condition. So let's try WXT and U is set as Q over sigma square, R minus 1 over sigma square, X over C minus R minus square, T minus T square, V sigma square minus 1/2 sigma square T minus T star. And this is actually the variable used by Black and Scholes. So I have a suspicion that actually Black and Scholes obtained this equation maybe before they published the paper, but it took for them to actually solve this equation. So I think they obtained this U and V, the substitution of variable after many trial and errors. v was defined as a square. So I made a mistake. So let's T W X T. Before we do that, W we assumed exponential R T minus T star Y some unknown function of U V. So this will be so we first differentiate this exponential part first. That gives R exponential R T minus T star Y U V, right? Plus exponential R T minus T star. We have partial U, partial Y, partial T, partial U, plus partial V, partial Y, partial T, partial V. This is a chain rule. I think we have learned this about many times, right? Chain rule. Because U is a function of xt, V is also a function of xt. So when you differentiate this y by t, you first differentiate by u, and then you differentiate u by t, and then you add by differentiation of y by v, and then you differentiate v by t. And so I wrote down u. Here's u. So u is sigma square r minus 1/2 sigma square ln x over c minus r minus 1/2 sigma square t minus t star. V was defined as 2 over sigma square r minus 1/2 sigma square t minus t star. So partial t partial u is only this part, right? So we have minus 2 over sigma square r minus 1/2 sigma square r minus 1/2 sigma square is minus 2 over sigma square r minus 2 over sigma square square. Partial t partial v is minus simply sigma square r minus 1 over sigma square. So partial t omega is equal to r omega plus exponential r t minus t star round u round y minus 2 over sigma square r minus 1 over sigma square square plus round v minus 2 over sigma square r minus 1 over sigma square square. Let me see. Oh, v was defined square, so it's square. Let me see. V so this equation 1. And right, partial t. So partial t was we have this is a square outside. So now partial partial omega is exponential r t minus t star round u, round y, round x, round u plus round v, round y, round x, round v. However, of course, u is 2 over sigma square, r minus 1/2 sigma square, ln x over c, minus r minus 1/2 sigma square, t minus t star. V is minus 1 over 2, r minus 1/2 square, t minus t star. So from this, we can see that partial x partial v is equal to 0, right? Because v doesn't contain x. And partial x partial u is simply logarithm, right? Two over sigma square r minus sigma square partial x partial ln x over c is 2 over sigma square r minus 1/2 sigma square 1 over x. So actually it's c over x multiplied by 1c. So it is 1 over x. So we have partial x partial omega is exponential r t minus t star partial u partial y times 1 over sigma square r minus 1/2 sigma square 1 over x. And if we differentiate it twice, what happens? We first differentiate this by u first. And multiply by this, 2 over sigma square. Plus partial y partial u. And you differentiate this minus x. 2 over sigma square r minus x square. So we have the following result. Exponential r t minus t star partial u square partial square y 2 over sigma square r minus 1/2 sigma square 1 over x square minus partial u partial y 2 over sigma square r minus 1 over sigma square x square. So we're almost there. So we have this result and this result. Oops. That's okay. It's not my thing. So, and we obtain, so let's summarize our findings. We did this for, go back to that part, partial t. R over sigma square over 2 square plus partial y partial v minus 2 over sigma square r minus 2 over sigma square square and partial x exponential r t minus t star partial u partial y sigma square over 2 r minus sigma square over 2 1 over x and partial x square partial square omega exponential r t minus t star partial u square partial square y 1 over sigma square r minus 1/2 sigma squares and x square minus partial u partial y 2 over sigma square r minus 1/2 sigma square x square. So what happens? R, W, Rx, Wx, W omega is exponential R t minus t star partial u partial y sigma square r minus 1/2 sigma square r, right? It cancels in the this x cancels in the x in the denominator. 1/2 sigma square x square partial x square partial square omega is 1/2 sigma square x square exponential r t minus t star. Oh, you have to be really patient. 2 over sigma square r minus sigma square x square minus partial y partial u 2 over sigma square r minus 1 over sigma square x square. Right. So I think this x will also cancel this x in the denominator. So if we arrange the terms, what we get is we have 1/2 sigma square exponential r t minus t star partial u square partial y sigma square over 2 r minus 1/2 sigma square 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 minus partial y partial u 2 over sigma square r minus 1 over sigma square. So let's add them together. You need more time to copy, right? So in the end, it doesn't matter which area you are solving. Engineering, physics, mechanics, or even finance. You're just solving the partial differential equations in different forms. We have obtained this, so this is 2. Right. I made the mistake while copying the equations. So should have R. Using this formula, let me check with the keep making. So RW minus Rx partial x partial W minus 1/2 sigma square x square partial x square partial square omega is RW minus exponential R t minus t star partial y partial u I think for your convenience, I think I could summarize here some result. Again, Rx partial omega. This is from previous page. Was exponential R t minus t star partial u partial y cos 1 over sigma square r minus 1 over sigma square and 1/2 sigma square x square partial x square partial square omega is 1 over sigma square exponential r t minus t star times partial u square partial square y sigma square over 2 r minus 1/2 sigma square minus partial u partial y 2 over sigma square r minus 1/2 sigma square. So use this result from the previous page. I still haven't figured out how to make a copy and paste from the previous page, so I'm doing it very hard way. So the first part is simply let me see, this 2, right? This partial x think this has to be 2. This has to be 2 over sigma square r minus 1/2. It should have r here. Make a mistake whenever I make a copy. Sigma square r minus 1/2 v square exponential r t minus t star partial u square partial square y 2 over sigma square r minus 1/2 sigma square minus partial u partial y 2 over sigma square r minus 1/2 sigma square is same as partial t, and where was partial t? Partial t was anybody remembers the formula? So partial t was, I'm going to put this here, rw plus exponential r t minus t star partial u partial y minus 2 over nu sigma square r minus 1 over sigma square plus partial y partial v minus 2 over sigma square r minus 1 over sigma square. Let me see. So let's compare the forms. So this cancels each other, right? And something is wrong with the formula. W. Right. So we have this square. So you can combine them to this together with this. What happens? So this and this, you can combine them together. What happens? We have a common factor r minus 1/2 sigma square 2 over sigma square r minus, something is wrong. check. Oh, right, we have this minus, this is sigma 1/2 sigma square. So 2 over sigma square r minus 2 over sigma square square, right? So if we combine them together, then we have this term and so let's compare these two. So minus what happens? Minus of 2 over sigma square r minus 1 sigma square r minus 1/2 sigma square 2 over sigma square with plus, right? This is sine plus r minus 1 over sigma square is actually minus 2 over sigma square r minus sigma square over 2 square. So it cancels with this, right? Oh, wow. So we have the following term. Minus sigma square exponential r t minus t star partial u square partial square y 2 over sigma square r minus 1 over 2 sigma square is exponential r t minus t square minus 2 over sigma square. This was, I think, square. Partial t was, this is a square. Right? If we go back, but I think I almost got it right. So we have the following. Minus 2 over sigma square r minus 1 over 2 sigma square. So what? This cancels each other. So what do we have? This is the same factor. This is the same factor, right? So this factor and these factors are the same, and this factor and this factor are the same, and there's a missing term, partial v, partial y. So after this transformation, what do we get? The simpler equation. this. So we have partial u square, partial square of y, partial t, partial v, partial y. So after this transformation, what we did is transform the original Black-Scholes equation into something different. And this one is actually well-known equation called heat equation. So he discovered that Black and Scholes discovered that the Black-Scholes equation is transformed into a heat equation. And the solution of which is well known. Since 18th century. So the Black-Scholes equation can be transformed into the simpler form called heat equation. And so maybe before I proceed, maybe you can take a break, because I think still you will be having trouble figuring out. Black-Scholes equation can be transformed into heat equation. And before we try to solve the heat equation, we can get some properties of a solution first. So U was defined as 2 over sigma square. Two T minus T star. V is minus 2 over sigma square, R minus 1 over sigma square, T minus T star. So boundary condition is at T is T star. It's called the maturation date. So when T become T star, then this is 0, right? This is 0. So we have V is 0, U is 2 over sigma square, R minus 1 over sigma square, ln x over c. So boundary condition was when x is smaller than c, then from this we can see that u is less than 0, right? When x is less than c, then any logarithmic value with a negative sign with the less than 1 is negative, right? So from this, u is less than 0, right? Then we set boundary condition is y equal to 0. When x is greater than c, u is 2 over sigma square, r minus 1 over sigma square, ln x over c. Or ln x over c is r minus 1 over sigma square u times sigma square over 2. And I need more space here, 3. Then x over c is exponential r minus 1 over sigma square u sigma square over 2, or x minus c is c times exponential this r minus sigma square u sigma square over 2 minus 1. So that's our boundary condition for 0. So in other words, the boundary condition is the following. Y u0 u0 Now we go back to the solution. We need to solve this partial v, partial u, y, right? Partial u square, partial square y. And we can use one condition when for less than at u is 0, y is 0, right? Y u 0, 0. So we can try a separation of variable technique. So y is some function of u only and function of t only. Then partial t, partial y set is called the separation of variable. That's one of the simplest methods solving partial differential equations. So partial v is xu tv dtv, right? And partial u square, partial square y is simply tu square t square xu tv, right? So if you're assuming that this y can be represented as a function of u only and function of t only, v only. This is a very ad hoc assumption, but we have to have something to start with. This is probably one of the simplest methods of solving partial differential equations. And then, if we differentiate y by v, then it's actually derivative of t by dv, right? Or if we differentiate y by twice by u, it's a differential of x by u twice. Then partial v partial y is partial u square partial square y. This is number 2. Or xu dv dt is same as dt square d square x tv. Tu, right? Let's repeat the last part. So let x u tv tv is same as t u square d square x u tv. And if for xu tv is non-zero, non-trivial solution, we divide everywhere by xu tv. So if we divide everywhere by xu tv, what do we get? xu over d u square d square xu equal tv dv dtv, right? So this part is a function of u only, and this part is function of v only. So left half side is a function of u only, and right half side is a function of v only. So how can that be possible? If left side is a function of u only, and right half side is a function of v only, only possible case is both are constant, right? It's the only possibility allowed, right? If the left half side is a function of u only, and right half side is a function of v only, and they are the same, then the only possible case is they are constant. So we can say some number minus lambda. Then we have the following: du square d square xu plus lambda xu is 0, with the boundary condition is 0. Or dv dtv plus lambda t v equal to 0. So say lambda is some alpha square, positive real number. We already have a solution. Then okay. x u is sine alpha u. That's the only possible case, right? And t v is exponential minus alpha square v. So general solution is all possible combination of alpha. So y u v can be written as the following: some constant exponential minus alpha square v sine alpha u d alpha. And we have the boundary condition. Remember that y boundary condition was the following: y u0 was 0, c exponential r minus sigma square over 2 u sigma square over 2 minus 1. That was the boundary condition. So we can set this, say f some function of u. Then y u0 is 0 to infinite 3 alpha sine alpha u d alpha is fu for u. Then G alpha can be actually found too. Need time. Then G alpha actually 2 over pi fu sine alpha u du. When fu G alpha sine alpha u d alpha. Actually, this can be this you have to believe me. This is Fourier sine integral. You can Google this. Actually, I can show this relation true, but it takes time. So let's just postpone it until to the end, maybe next week. Let's just try to find out the solution. Then y u v is pi over 2 d alpha exponential minus alpha v sine alpha u fs sine alpha s ts. So it becomes 2 over pi 0 to infinite d alpha ts exponential minus alpha square v f of s sine alpha u sine alpha s. This can be decomposed using same as 1/2 cosine alpha s minus u minus cosine alpha s plus u and we have one more integral that is exponential infinite alpha a cosine alpha b d alpha is 1/2 pi over a exponential minus b squared over 4a. Actually, this integral is easy to derive. So we can say alpha b d alpha is both an even function, so we can actually say 1/2 minus infinity to infinite exponential minus alpha square a cosine alpha b d alpha, right? Because cosine alpha something is always even function. And then this is actually real part of this exponential I alpha b, right? Real part of exponential minus a alpha square minus a over I alpha b, right? D alpha minus plus 1/2 real exponential minus a alpha minus 2a over ib square, and this is same as minus a times a square alpha square b square d alpha. Oh, no alpha, b square, 4a. So that is exponential minus 4a over b square, 1/2 real exponential minus a alpha minus 2aib square d alpha. And we know this Gaussian integral, right? I think I derived in the first semester that alpha x squared dx is root pi over a. That's called Gaussian integral. Anybody familiar with the Gaussian integral? Raise your hand. At least I think I derived in the spring semester, but you're not familiar? Okay, I'm going to do that. Okay, so then whole part is same, so this goes to here, 1/2 root pi over a exponential minus 4a over b squared. And because you may not be, if you're not familiar with Gaussian integral, I can do this. So for your benefit, I will do Gaussian integral. Say I is minus infinity to exponential minus ax squared dx. I squared is y squared dy, right? So it becomes minus infinity to infinity x squared plus y squared dx dy. We can change it into polar coordinate. Rho square is x squared plus y squared. Then dx dy become rho d phi, right? So into polar coordinate. So it becomes something like this, 0 to 2 pi, 0 to infinite, exponential minus I rho square, rho d phi. Is 2, it can be written as 0 to infinite, exponential minus a rho square, rho d rho. So say x is rho square, dx is rho d rho twice, right? So rho d rho is twice over dx. So it becomes pi times infinite to infinite exponential minus ax dx. It becomes, if we integrate this, what happens? Pi over a, right? So I is square root of pi over a. So that's the Gaussian integral. So let's go back to the solution. We have this knowledge. So exponential minus alpha square v sine alpha u sine alpha s t alpha. Let's do this integral first. Is 1/2 exponential minus alpha square v cosine alpha s minus u minus cosine alpha s plus u t alpha is 1/2 exponential minus alpha square v cosine alpha s minus u t alpha minus 1/2 exponential minus alpha square v cosine alpha s plus u t alpha. So this is A, this is B, this is A, this is B. Then we have the following: 1/4 pi over 3 exponential minus 4v s minus u square minus 1/4 pi over 3 exponential minus 4/3 s plus u square. So we have the final solution. So u3 is 1/2 pi times t alpha ts exponential minus alpha square v sine alpha u sine alpha s fsts. So if we substitute this into this, then we're too fast. So I will let you copy. Let's make some calculation. 2/pi times 1/4 pi over v is 1/pi v. Right? So can I move on? So y u3 is finally, we have the following: 1/2 pi v 0 to infinity fs exponential minus 4v s minus u square 4v s plus u square. The first integral, say 1, 2. So let's start with 1. So 2 root pi v s exponential minus 4v s minus u squared ds. So we introduce r as s minus u 2 root 2v. dr is 2 root 2v ds. ds is 2 root 2v dr. S is u plus r 2r root 2v, right? With the following change of variables, then we have, this becomes 2 root 2 pi v times 2 root 3, and when S is it becomes infinite to R become S become U plus 2r root 3 exponential minus r squared dr, and when s is 0, r becomes minus u over 2 root 2v, and this cancels this cancels this, so become 1 over root 2 pi infinite minus u over 2 root 2v f u plus 2r root 2v exponential minus r squared dr. On the other hand, the second integral, I think we are almost there, maybe 5 more pages. Second integral, can I go on? Second integral is the following. Pi v 0 to infinite f of s exponential minus 4v over s plus u squared ds. So we have changed it into something different, s plus u 2 over root 2v. S is minus u plus 2 root 3 r. ds is 2 root 3 dr. So it becomes 2 root 3, 2 root pi v. When 0, this becomes u over 2 root 3 over infinite f over u plus 2 r root 3 exponential minus r squared dr. By the way, y u0 is f over u is become 0 to c u is less than 0 exponential u sigma square over 2 r minus sigma square over 2 minus 1 u is, this is a functional form. So we have the first this part minus u, right? So yuv is root 2 pi over minus u 2 root 3 over infinite f u plus e to r over root 2 v exponential minus r squared dr minus root 2 pi u over 2 root 2 v infinite f minus u plus 2 r root 3 exponential minus r squared dr. So if we take a look at this, when u is increasing, this part becomes negative, right? This whole part. As u increases, because we have minus sign, so when u is 2 root 3 is 0, and if u is larger than that, this value is 0, right? So according to the boundary condition, when u is equal to 0, f is 0, right? So actually this integral can be ignored. So this whole thing is 0 because fu is 0 for u is less than 0. So we need to worry about the first integral. So y uv is root 2 pi minus u over 2 root 2 v f u plus 2r root 2 v exponential minus r squared dr. For let's say set r over q over 2 root 2 dr is square root of 2 over tq. Then it becomes root 2 pi minus u over 2v. F is c exponential. Where is it? So u become u plus q. So this becomes q root 3, right? Become 2 root 3 root 2v times sigma square divided by r minus sigma square over 2 minus 1 exponential minus q square over 2 dq. Oh. Now, V was what? Minus 2 over sigma square r minus 1/2 sigma square t minus t star 2 over sigma square r minus 1 over sigma square t star minus t, right? So 2s 2v is 4 over sigma square r minus square t star minus t, or root 2v 2 over sigma r minus 1 over sigma square root of t star minus t. And u was 2 over sigma square r minus 1 over v square sigma square ln x over c minus r minus 2 over sigma square t minus t square. So root 2v over u is 2 over sigma square r minus 1/2 sigma square ln x over c minus r minus sigma square over 2 t minus t star divided by 2 over sigma r minus 1 over sigma square t star minus t is sigma square root of t star minus t over ln x over c minus, or we can change it r plus minus sigma square over 2 t star minus t. So let's set this as a value as d2. And u plus q square root of 2v is square r minus sigma square ln x over c minus r minus 1/2 sigma square plus sigma over tq r minus sigma square t star minus t. So you can combine them together with the following: sigma square r minus 2 over sigma square ln x over c minus r minus 2 over sigma square t minus t star plus q sigma root t star minus t. So I'm actually calculating for the exponential factor. So almost done. So u plus q square root of 2v 1 over sigma square divided by r minus 1 over square is, from the previous result, we have 2 over sigma square r minus 1 over sigma square ln x over c plus r minus sigma square over 2 t star minus t plus sigma q root t star minus t 1 over square square r minus sigma square over 2. So this cancels this and this cancels this. So we have the following: ln x over c plus r minus sigma square over 2 t star minus t square plus q sigma t star minus t. So exponential u plus q root 2v sigma square over 2 times exponential minus q square over 2 is actually ln x over c plus r minus sigma square over 2 square root 2 over t star minus t square plus sigma q t star minus t minus 1 q square. And this becomes so it's almost one-page calculation, and I'll leave it as homework. So it can be a quiz problem as well. So it becomes exponential ln x over c plus r t star minus t exponential minus 1/2 q minus sigma root t star minus t square. Oh. Well, I guess it would be difficult to get a Nobel Prize. So I'm following this exactly the same way that the Black and Scholes paper. So this analysis actually got them, the Scholes Nobel Prize. So it may be a good opportunity to observe that maybe someday one of you might discover new equations in which field, I don't know, and maybe get a Nobel Prize in 40 years later. So let's do this part. Square root of 2 pi minus u over 2v infinite c exponential u plus q root 2v 1 over v square divided by r minus sigma square over 2 exponential minus q square over 2 dq it turns out to be square root of 2 pi minus, this is minus t2 infinite. We derived this as a t2, previous page. C exponential ln x over c plus r t star minus t exponential minus q minus sigma root t star minus t square dq. So it becomes c times exponential ln x over c is x over c, right? So it becomes c over x exponential r t star minus t square root of 2 pi, and it become q prime. Then this will become minus t2 minus root sigma t star minus t infinite exponential minus q star square tq star. So t2 sigma root t star minus t is sigma root t star minus t ln x over c r minus sigma over 2 t star minus t plus sigma square t star minus t becomes sigma root t star minus t ln x over c plus r over sigma square over 2 t star minus t. Let's say t1. So this integral actually becomes x times exponential r t star minus t square root of 2 pi minus t1 over infinite q square dq. And second integral is the following. I think I probably should have let you copy. The another integral from the boundary condition is the following. We have square root of 2 pi minus u over 2v infinite c exponential minus q square over 2 tq is c times square root of 2 pi minus t2 to infinite exponential minus q square over 2 tq. So y uv becomes x exponential r t star minus t square root of 2 pi minus t1 to infinite exponential minus q square dq minus c square root of 2 pi minus t2 to infinite exponential minus 2 over q square dq. So finally we obtain the option price function. xt is exponential rt minus t star yuv, right? And you can go to next page. You need to copy. 오늘요?
예, 왜 이게 리니어 콤비네이션이 아니라 왜 인테그랄의 합으로 주어지?
리니어 콤비네이션이 결국 인테그랄이지.
근데 그러니까
알파가 연속이네.
그래도 그 시그마의 합과 인테그랄의 합은 분명히 아무리 무한대로 간다 해도 약간 값의 차이가 났어.
그러니까 사실은 이제 알파를 모르잖아요.
예.
알파는 이미 연속적인 값이거든.
네.
그러니까 연속적인 값들 stay. So I'm going to write it again. xt exponential r t minus t star y uv is exponential r t minus t star x exponential r t star minus t square root of 2 pi over minus d1 to infinity exponential minus square of dq minus c exponential r t minus t star square root of 2 pi minus t2 infinite exponential minus 2 over q squared dq. So we can simplify this function. So this is tabulated function, and so we define nz 2 pi over minus infinity to z exponential minus 2x squared dx, the same as minus c to infinite exponential minus 2 over x squared dx. It has a name called this cumulative distribution. Of standard normal value. You may have encountered this during your statistics class in high school. I don't know, 정규분포 or something like that, right? Then x n t1 minus c exponential r t minus t star and t2. That's the conclusion that the Black and Scholes obtained in his paper. So this shows that the optimal option price can be determined from the solution of the Black-Scholes equation. And t1 and t2 were here. t1 was where was t1? t1 is sigma root t star minus t ln x over c plus r plus sigma square over 2 t star minus t. t2 was sigma root t star minus t ln x over c r minus sigma square over 2 t star minus t. So everything is known except sigma is a parameter. So when you determine the option price, you can still tune the value by tuning the sigma value as a parameter. Interest rate is given, right? So in each year, the 한국은행 they announce the interest rate. So you can use that value. And maturation date is determined by the contract. So you can set. The only thing you need to determine is the sigma, which is fluctuation related, the variance of a stock price. Okay, so this is about the covering the famous Black-Scholes equations and its solution. So I'm following pretty much the same way as Black and Scholes did in 1973. And they got the one of the guy got the Nobel Prize because of this formula. And next week we are going to have a quiz, right? 2-hour quiz, including this part, today's class. And so you can prepare 2-page cheating sheet. And so we are going to have a quiz first, right? With after class. Which one is better? Have a class first and then have a quiz, or quiz first and then have a class? Quiz first, right? So next week, November 20th, page number 3, for 2 hours. So you can prepare 2-page cheating sheet. 2 hours. So So main topic is one is the integral with the residue, and second part is partial differential equations, and probably the topic covered today. So it will be fun, 2 hours. 수리경제 할때 배웠었나 이거?
근데 너무 빨리 나가서.
이 정도로 다 배웠어?
네, 근데 3-4주 약이었어요.
오늘 한 게?
네.
3-4주 동안 이걸 하는 거야?
왜냐면 옵션에 뒤에가
2페이지.
앞뒤로 그냥 한다고 해서.
예, 그렇죠. 예, 앞뒤로. 옵션에 대한 거.
그래서 처음에 되게 옵션 저 처음에 뭔지 몰라가지고
네.
그 앞에 저희 수업한 거에서
I think I'm going.